Pluto, a far-off and jumbling, more unassuming planet, was once a solitary individual from our planetary gatherings planetary family. At any rate, later, upsetting articulations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight with an amazing openness. They suggested that this cold world is on a potential pact illustration with Neptune. But how is it that this could work out? Additionally, what might be the consequences of such a huge event? Are we seeing an intriguing affected eccentricity? Or is there something else to this coming boundless mishap? Join us as we inspect the potential consequences of a Pluto-Neptune influence. Pluto, a previous planet that was limited to a more modest individual planet midway in view of its intrigued circle, remains a subject of interest and study in the galactic community. As per continuous figures by leading experts, Pluto's course is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm of a potentially dangerous mishap between these two planets that could be in immense peril to Earth. But how is such an event even conceivable? Pluto's endeavor around the Sun isn't typical for any other planet in our nearby planetary system. It requires a stunning 248 years to complete a single orbit. This suggests that, since its discovery in 1930, it hasn't even completed one full orbit. However, the interest doesn't stop there. Pluto's way is defined by its significantly bended shape, going completely from the nearly round orbits of the huge planets. What makes Pluto's orbit significantly more astounding is its inclination, still up in the air at 17 degrees to the ecliptic plane. The manner in which Pluto follows is considerably more outrageous compared to different planets. This inclination and unusualness add layers of multifaceted design to its orbital pattern. Perhaps one of the most charming aspects of Pluto's orbit is its blending with Neptune's for something like 20 years in each orbit. Pluto actually draws closer to the Sun than Neptune, contradicting what we would expect from their circumstances in the planetary group. This prompts the ordinary question: why hasn't Pluto banged into Neptune? The answer lies in the gravitational effects of various planets. The examination of Pluto's orbit began not long after its discovery. Initially, space specialists fought to get a handle on its uncommon way in contrast to various planets, whose orbits lie fairly near the ecliptic plane. Pluto's orbit stood apart with its problematic inclination and erratic shape. The mystery reached out with the affirmation that Pluto's orbit, in the grand scheme of things, does indeed cross Neptune's. The persistence of Pluto's orbit in the midst of these complexities is proof of the intricacies of celestial mechanics. The three-body problem in space is about figuring out how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like attempting to guess where they will go considering where they start and how they pull on one another. In Pluto's case, this issue shows how its orbit, Neptune's orbit, and the Sun's gravity all interact in an obfuscated way. Terms like asymptotic libration, scope libration, and the VZK wobbling are part of this conundrum. According to astrophysicists, what's keeping all planets in their orbits is a kind of libration with respect to Pluto and Neptune. This term infers that at any point Pluto crosses Neptune's orbit, its position is consistently something like 90 degrees away from Neptune. This spatial partition is significant in holding their orbits back from influencing each other. Scope libration, on the other hand, implies the vertical movement of a celestial body in its orbit. For Pluto, this suggests that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbit plane, contributing an extra layer of protection from potential impacts. Another essential factor in this scenario is the VZK wobbling. This is named after three researchers, V. Apple, L.V., and K.U. who studied how things move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This pulling influences how they move, and for Pluto's case, VZK helps us understand the reason why its path near the Sun is so unusual. Despite the apparent bedlam, this influencing helps keep Pluto's orbit stable for an exceptionally critical time frame. The VZK wobbling shows that, although things in space could seem wild and inconsistent, certain patterns and rules help keep everything in place. These factors help maintain Pluto's orbit, ensuring it doesn't collide with Neptune or veer off course. This three-body issue has an impact on understanding how these orbits change due to how space objects pull on each other. Focusing on this helps us study Pluto, our neighboring planetary system, and distant stars and planets. Mathematical simulations in the late 1980s revealed that, despite these consistent properties, Pluto's orbit is actually wild, with minor deviations in initial conditions leading to significant differences over a long period of time. However, these unusual properties of Pluto's orbit have been found to maintain consistency over extremely long periods of time. Later computer tests have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only factor. Jupiter's gravity also plays a huge role in protecting Pluto's orbit. What's more, Saturn helps in that general area as well. These tests show that Jupiter's gravity alone is powerful enough to ensure Pluto stays on a reliable path for an incredibly long time, potentially even billions of years. Perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto can continue moving safely in space without running into trouble. These eccentricities are vital in the larger context of the universe for maintaining the control and consistency of celestial bodies. Without these factors, the nearby planetary system, as we likely know it, would be a place of much greater conflict and instability. Bodies like Pluto could indeed collide with others or be ejected from their stable orbits, triggering a cascading effect on other celestial bodies. For Pluto, particularly with discussions about it possibly colliding with Neptune later on, understanding its orbit is critical. This gives us a clearer picture of the neighboring planetary system's dynamic nature. The case of Pluto illustrates how even the most apparently unstable orbits can achieve a state of harmony through the complicated interaction of gravitational forces and orbital mechanics. It also shows the importance of consistent insight and analysis of these idiosyncrasies to more readily make sense of our place in the universe. Exploring the depths of space often leads us to confront the unconventional nature of celestial bodies, and Pluto's orbit is an ideal example of this unconventionality. The idea of orbital resonance, which implies the sensitive dependence of a celestial body's orbit on its initial conditions, is clearly outlined in the case of Pluto. This means that even slight variations in the small planet's position or speed can significantly alter its long-term orbit. Using virtual simulations has been incredibly valuable for research to understand how Pluto moves in space. These simulations use complex math to model how Pluto, along with other space objects like Neptune, pull on each other. By changing small details in the simulations, astronomers can see how even tiny changes can make a huge difference in where Pluto ends up. In the late 1980s, these simulations revealed something truly fascinating about Pluto's orbit. Despite having systems like asymptotic libration and scope libration to keep it stable, its orbit can still be wildly unpredictable. If you start with even a tiny difference in where Pluto is or how fast it's moving, over many years its path could end up looking very different. Despite this chaos, Pluto's orbit remains stable for billions of years. This suggests that Pluto's journey around the Sun has a certain order to it, even though it appears chaotic at first, particularly when it involves tumultuous orbits like Pluto's. This presents enormous challenges. The inherent nature of these systems suggests that long-term forecasts are often filled with uncertainties, while mathematical simulations provide a powerful tool for understanding and predicting the future behavior of celestial bodies. They also highlight the limitations of our predictions. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight mistake or deviation can drastically change results, making accurate predictions a daunting task. Moreover, the turbulent nature of large orbits like Pluto's serves as a reminder of the ever-evolving and dynamic nature of the universe. While we have made enormous strides in understanding space, the example of Pluto reminds us how our understanding of the universe is still limited. Understanding the gravitational effects of the giant planets on Pluto's orbit offers valuable insights into the broader dynamics of the nearby solar system. It shows how the presence and position of each planet can have sweeping effects on the stability and direction of various bodies within the system. So why are prominent astrophysicists suddenly raising concerns about a potential collision between Pluto and Neptune, despite all these complex forces attempting to prevent such an event from happening? Neil deGrasse Tyson, a renowned astrophysicist, offers a book-length perspective on the mysteries of our nearby planetary system, particularly the intriguing example of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, provides insightful analysis on the developing nature of celestial mechanics and the public's interest in the neglected corners of space. The situation on Pluto's renaming is outlined in the ever-expanding data on our nearby planetary system. He considers the renaming to be not a diminishment, but rather a necessary change, in line with our growing understanding of the many bodies surrounding our Sun. Tyson's approach to celestial mechanics is one of continual learning and adaptation. He sees the intricacies of Pluto's orbit, as well as its interactions with Neptune, from a perspective that acknowledges the unpredictability of space. He suggests that while Pluto's orbit is stable for now, it could undergo significant shifts in the future. This possibility serves as a reminder of how much we still need to discover about the forces shaping our nearby planetary system. All in all, Pluto's orbit is an enthralling case study in the complex interaction of gravitational forces within the nearby planetary system. While its path is stable at the moment, the mysterious dynamics between Pluto, Neptune, and the other planets suggest that even the most seemingly stable orbits could change over time. As astrophysicists like Neil deGrasse Tyson continue to explore the secrets of the universe, they help us better understand the delicate balance that governs the movements of celestial bodies. The potential for a Pluto-Neptune collision is not necessarily inevitable. However, it's a reminder of the constantly evolving and enigmatic nature of the universe. Despite the established theories surrounding Pluto's orbit, it's important to consider the broader consequences of these dynamics for how we understand the nearby planetary system and the universe at large. While Pluto's journey is one of fascination, it's also a reminder that the universe is full of mysteries and complexity, waiting to be explored. The idea of orbital resonance, particularly between Pluto and Neptune, is a fundamental piece of the puzzle. This resonance, where the ratio of Pluto and Neptune's orbits is 2:3, is a critical component of celestial mechanics. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This ratio ensures that, even though their orbits cross, the 2 planets never collide. This is a result of the gravitational interactions that stabilize their paths, working together to prevent any catastrophic effects. The importance of resonance in maintaining stability cannot be overstated. It provides a perfect example of how systems in space, even those that initially appear chaotic, can self-regulate through subtle gravitational forces. Understanding this resonance also explains why Pluto, despite its eccentric orbit, has remained stable for billions of years. This quirk is a crucial aspect of the nearby planetary system's larger structure. The effects of planets like Jupiter, Saturn, and even Uranus are vital in maintaining stability in the orbits of smaller bodies like Pluto. Jupiter, with its immense gravitational force, acts as a kind of safeguard for the interplanetary system, influencing the paths of various asteroids and other dwarf planets, including Pluto. In fact, some scientists speculate that Jupiter's gravity may have kept Pluto from being ejected from the solar system entirely. Without Jupiter's protective effect, Pluto's orbit might have been disturbed even further, potentially sending it out of the Sun's gravitational influence.